So the just so you can get ahead of this, the one prerequisite is to I would advise you to have a Google account. Again, not a paid, but a free Google account, because the code notebooks we're going to be using and some of the materials we'll be looking at today are stored in that publicly available Google Drive. All right, everyone, welcome to our machine learning data prep with Python. And last week we talked about why Python. And this week we're going to take that a step further. We're going to take the Python coding we learned, and now we're going to apply it to a very important problem, which is machine learning data prep in Python. And again, you can see this nice little DALL-E 3 image we prompted out here all around data cleaning, feature engineering, which we'll talk about later, and fine tuning and all that good stuff. So we'll get on with that. And you may have heard this phrase again many times, but it is so important. I just gave a talk at Bentley University down the road in Waltham to their masters in data analytics and their business analytics field, and I really think that's a great field to be in. People say that job's going to be replaced. I do not believe that, because cleaned, well-prepared data is the water that flows through the pipes of what is AI and machine learning. And, you know, think of AI, and when you're able to code up AI by writing a prompt and it builds all the code and the models for you, the most important thing is understanding what's going into that algorithm and what's coming out of it, right? And what's going in is this data, and garbage in, garbage out. And yeah, we know that. I talked about that. A lot of most machine learning algorithms, even LLMs that require text inputs, are still converting that text into what we call embeddings. And yeah, the main tool we're going to focus on today is a very famous one. It's called Pandas. It's the Pandas library, and that is been prolific for the last decade. If you go into any data science or AI shop, chances are they're using that Pandas library from West McKinney. And we can use that to read, clean, manipulate tabular data. We can read in data, fill the data group by. We'll also use NumPy, which is another famous library that helps convert numerical computations. We looked at one last week where we're using, instead of using a list, we're using an array. An array is not a native module in Python, but it is in NumPy. And then we look at some fun stuff like beautiful soup. So we're going to have actually a lot of fun today, and we're going to do some visualizations as well, because we always say in data science and AI, data storytelling and telling stories with your data is a really important skill. So we'll be looking at all this. Scikit-learn, we won't touch upon that until Thursday when we actually do some machine learning modeling. So that is key. And yeah, so I would advise you to learn Pandas, even though you can go to a prompt, such as within Colab, you can say, hey, build me out, profile this data for me. It will do the work for you, but most likely it will use a tool like Pandas. So if you are actually using AI to write your code, how are you to know if it's doing the best possible thing? So I would, again, you're taking this course today, that's great, but I would also encourage you to read the Pandas API and look at what's going on there. And it's famous for containing very well designed data structures. So the data structures we have native to Python, such as a list, a tuple, a dictionary, they're pretty basic. Of course, you have objects and classes you can build, but data frames, it's almost like you can do this matrix math and matrix manipulation. Imagine just basically having a spreadsheet and being able to put that spreadsheet into a piece of code. That's what you'll see Pandas gives us, and it's pretty powerful. And it does simplify those complex tasks of cleaning and pre-processing. And very importantly, it integrates with some other libraries such as NumPy, Matplotlib, making it very, very easy. And the idea really here is it doesn't matter if you're, let's say you have a spreadsheet file of 10,000 rows or 3 million rows. You can load it into pandas. It kind of breaks down around 5 to 10 million rows, depending on the size of your machine you're using. But if you've got millions of rows, you can literally, using code, act on every single row for a given function you want to apply to it. And that's a very, very powerful concept. So if you're doing feature engineering, you're looking for features, you're trying to do data profiling and whatnot. So that's kind of key here. So let's actually get into coding, because I do want to kind of make this a practical hands-on session. So I want to go to the first notebook, which is here. And again, some of you are joining us for the first time. So what I'm going to do here is, here's the link to the first notebook. And again, tell me if you're having any problems with it, because I just want to show you this notebook. This is a refresher notebook. So some of the core data structures that are essential for data cleaning. And sorry, I should also note, when it comes to data science and AI, I should include this slide. But if you talk to anyone practicing data science or machine learning, AI might be a little different depending on the job function. But with machine learning and data science, up to 70% of your job role is in actually profiling and cleaning data. And I know that sounds very strange, because most of the time when you're playing around in data science, someone gives you a perfect data set. In the real world, that doesn't work. First of all, you have to learn the data. Let's say you go into a real estate company. I don't understand the business of real estate. How do I understand this data? You have to take time in that. You might be working for a healthcare company, finance company, advertising agency, who knows, right? You have to learn the language of that data, the domain expertise to understand how to interpret that data. That's number one. It's going to be stored in all kinds of formats. It's not going to be a spreadsheet. It's going to be probably stored in a relational database, structured and unstructured. And then you have to take that data, understand, as we talked about last week, what are the features? What are the things I can predict with this data? Is there missing data? So believe me when I tell you, anywhere from 50 to 70 to 80% of your time can be done working with the data, which is good news actually, because data science and machine learning can be quite difficult field to master, especially when you think the math and the statistics involved and all the algorithms. But if you're doing something as simple as arranging data in a spreadsheet, that's not too hard to master. And it actually is quite interesting work, and it's not that difficult. So really don't treat this as something that I should rush through this as quickly as possible, because I want to get to the algorithms. I want to get their predictions. It's kind of like Andrew Ning says now, like the algorithms are so good now that yes, you will get some better model performance by tweaking the parameters or the hyperparameters. But really what it comes down to is how good do you understand the data and how well are you at cleaning that data. So that's why you find if you go for an interview at Google or Meta, they'll ask you to walk through a data set or a problem. They're not asking you to straight go and figure out, well, this data is linear or non-linear. I should be using a regression model, or maybe I should be using XGBoost or random forest. No, they're trying to figure out, well, how would you, if you were given a data set, just handed one, no explanation, how would you go work through understanding that data set? What are some of the problems inherent to that data set? So that's, again, why I encourage you to read that. Where did my data literacy go? Read that data literacy course if you haven't. So again, I should have, what I always say, this is a motivating example. I should have mentioned my motivating example at the very start, but trust me, this is so core to the job. And data is always kind of contained in the structure. It's not in the ether. We need to store this. We need to be able to view it. We need to be able to profile it. So this refresher notebook, which again, if you're not familiar with Python, our programming languages, go review this again. We covered this all last week. These are some basic data structures, which you're going to be seeing a lot in these notebooks. We have a list, which is just a basic list of items. For the most part, it should be homogeneous, meaning it contains the same data type. This is mostly a list of strings, and you can access the strings with indexing. And the next one we looked at is Yeah, this is a quick example of manipulating those strings. So look at that if you don't understand it. Zero indexing. Remember Python, we always start with zero indexing. So if I have 3 items in my list, item 0 is the first item, item 1 is the second item. So make sure that doesn't throw you off. This is a tuple. It's an interesting little data structure, which I don't use a whole lot, which is a refresher on that. And then a dictionary, which is something more useful, which encapsulates that very important computer science paradigm, which is key value pair, right? You'll encompass this all the time. If you actually ever read the LLM, Attention is All You Need paper, this kicked off this LLM, you hear about QKV, which we'll cover in a couple of weeks, which is the query when you query a piece of text. And then the KV is the key and the value. So key value pairs. So take a look at this again, because you'll see this throughout these code notebooks, and a little exercise there. So good. So with that, unless there's no more questions, we'll get right into the first notebook. And the first notebook, again, is here. So you're not following along that drive here. Here's the first notebook. Let's get started with our first notebook. So that's actually not our first notebook. That's yeah, lesson 1. So lesson 1, I briefly mentioned pandas and how powerful it is. So in this notebook, we're going to go over pandas and understand how to build one. And again, the first thing we want to do here is actually import that library. We're using a Google Colab, which should be familiar to you. And a Google Colab is markup text, which you can edit yourself. And then we have these code cells here. So again, I would encourage you in your own time to play around with these code cells, run them yourself, understand what they're doing here. And basically write in your own code if you want to add new values there and understand how that works, and et cetera, right? And first thing we have here is the pandas library. And we want to create a list. As you can see here, this is a list as we said before. And from that, create a series, which is actually also in that, I didn't talk about it much, but it's also in that other one here. And then from that series, we want to further on create a pandas data frame. So let's just refresh quickly on this is a list. And from the list, we can create a series. And again, same as last time, if you mouse over this, you should be able to see what these values concern. So this is a list. We're creating a series, and then we're just printing out the series based on the location. So this is the first location. This is the third location, right? So first location is 5,000. Third location is 4,500. And remember from last week, again, we had to look label-based access and indexing-based access. So if we want to look up something by street address, that would be a label. If we want to look it up by index, that would be a number between 0 and whatever number of values are stored in that list or series. So want to skip ahead to this here because I want to show you in a series a very important thing we can do is by default the index is the numerical index, but here what we're doing is we're creating this list. We have 2 lists here. One is the price list, one is the addresses, and we're creating a price series. And what we're telling it to do is instead of using numerical index, use addresses as the index here by using this parameter here. So create a series with a custom index label. So now what we can do here is when I print it out, notice how the index is no longer 0, 1, 2, 3, 4. The index is actually the address. So that's pretty cool because if you have a massive database with thousands of points of on a customer, maybe their index is their customer ID, their social security number, or their street address. So that's how a lot of modern data structures, data stores work. They use some kind of an index that's not some random numerical number to look up your information. And what we can do now is we can use this address here. If I have it right, did I run this? No, I didn't run it. We can use this address here to find the location. So what is stored at the, what's the price of the house at 321 Pine Street? And 321 Pine Street is $70,000, and that prints it out here. So again, we're using dot notation here. So if you haven't joined us, if you're just joining us for the first time, when we use dot notation, it allows us to fill in these different methods. That's index location and location lock is the one we're just showing here. So you can see here, you can find those methods pretty easily using that dot notation, which won't work unless I fix it there. And this is more or less the same, just showing you some more indexing. So what you can also do in a series is interesting. You can drop these functions or methods, and using square brackets, just look up the location value using one of the two indexes, right? So here we're accessing it by position, and here we're accessing it by index, label index. So you can see here, we're again printing out the series here, and we're saying what's the first row, which is 5,000, gets printed out, and then what's 123 123 Main Street, which is also 5,000. So if I had put in something like 654 Maple Street, it would print it out different value, 55,000. So again, it seems very simple, but trust me, when you're doing this programmatically and at scale, you won't have a little simple toy example like this. You might be running through an index, a list of 50,000 addresses, and having to act on all that stuff to say, let's do some kind of feature engineering on that. Now, again, imagine if you had, actually, let me show you something here. If I can open this. To give you kind of a real example, I know this is kind of hard to see. Let me open this with Google Sheets, be easier to see. A lot of times when we're in a spreadsheet, we might want to slice the data, right? So when we talk about slicing, for some reason, we might want to get this slice of data here. If you can see what I'm highlighting, right? Like, let's say we just wanted this slice of data, or I wanted two slices of data, like 2 columns of data, but only 1,000 rows. So pretty common thing that you want to do in a spreadsheet. And there's a way to programmatically do that as well. We call that slicing. And what we do here is we give it some kind of a range, just like you would do it in do that in a spreadsheet. You give it some kind of range of parameters what you want to slice on. And how we do that is, let's say again we had a series here. These are the values. This is the labeled index A, B, D, C. We can actually say, give me everything between label B and D, and it prints that out. So you can say it's going from B to D. And notice that D is exclusive, not inclusive, meaning it, for whatever reason, Python does this. Whoever coded this in Python, it only gives you out the values of B and C, right? So that is pretty important because you might be working on some pretty big data slices. And we'll talk about filtering later. So this is more like pretty much like column filtering, but we'll talk about filtering on the actual values of row in a little second. And another interesting thing about a series is, and I'll tell you a little bit why we're focusing so much in series. But again, imagine a series as being similar to a sheet in a spreadsheet. Another reason why I want to use a series is we can do all kinds of operations on it. So in a spreadsheet, if I wanted to add something here, I would have to maybe add another column, put an equals to sign, put a value here. Kind of cumbersome, but with code, I can basically take a single column. If I have a price column, I can add 1,000 to that, 10,000 to it. Or for a given column, I can calculate the mean, the sum, and other values. I can sort the values, I can sort the index, and I can replace the values. So you see here, what I'm doing is I've got the series I defined earlier, 10, 20, 30. We're adding 10,000 to it. We're calculating the mean, calculating the sum. We're doing a Boolean filter here based on various values. So what I'm doing here, if I slow down a bit, is I'm saying, show me everything in the series that has a value of greater than 10. And also you can apply another method to it, such as a sort index, sort by values, sort by index. We can also replace values here as well. So what I'm saying here is for the first row, sorry, the second row, because it's index of 0. For the second row, replace the value with 71,000 on it. And in this example here, we're just printing out cities, and I'm asking it, well, give me the unique values. And you can see here, Boston is mentioned twice. And down here, it's just printing out unique values. And then another great thing about this is you can apply functions across the entire data set. So I'm telling it here, for a given row or for the entire data set, change the text from lowercase to upper, which you saw it did here, right? So pretty powerful little techniques you can apply against various rows. So any questions on that so far? Because again, I know I'm going through this pretty quickly. Oh yeah, good question. Will they charge you for any of these notebooks? No. Sorry, I always go through a little spiel on class 1, but this is your first class. No, I do not have a paid account with Google. They will only pay it to you if you switch the runtime type to a paid CPU, like this is a GPU, graphical processing unit. So an A100, T4, L4, but you're just running this on the cloud. If you run too many sessions, it will ask you to close them down, but we're running on a free version. Yeah, I would definitely give you a heads up if it was something charging you. So the series is very important. It's a very important data structure. Yeah, Max, so let me highlight some questions here. So yes, you can create a series, you can have a sub-series, you can play around with that. But I would say don't focus too much on a series because we're going to use something even more powerful, which is a data frame. Because the series, for various reasons, which I want to get into, it's a bit limiting. So we're going to use something like a data frame, which really is more like a spreadsheet. So if I want to add in a column here, I can insert columns, I can insert rows. So think about a data frame, again, being your tabular data like you would see in a Google Sheet or an Excel spreadsheet. And they are much more powerful than a spreadsheet. So now we're getting to use the what I like, which is my favorite data structure within Pandas, which is a data frame. And for the most part, I would be using something like this. And there's various ways to create a data frame, but generally speaking, you want to give it data in a format similar to this. I can definitely have, blank cells, missing values. That's okay, because we're going to be looking at it later. But it's going to be some kind of a matrix or vector matrix similar to this. And with a data frame, various ways to create it. You can create it using an API, uploading a CSV file, which we'll look at. But right now, I'm just going to create a simple data dictionary. And a data dictionary is a good way to start with it because remember key value pairs. So this is the key, address key, price key, and here are the values. So the key is a string, the value is a list. So if I run this, and you can see here my, come on, highlight it. See my type is the dictionary, DICT. I have 5 items, and those items are a list and a string value for the key and value and key, respectively. And now when I print out my data frame, see the way I've printed this out in a nice tabular format. The print statement knows to just format in a nice format. So now I've got something that looks like columns and rows in a spreadsheet. And of course, what I want to do that, I want to, as Maxime mentioned, I want to be able to slice and dice, filter and sort, much like I would in a spreadsheet. So let's look at some of those here. First thing in a spreadsheet is I want to address one column. I can say DF address, and it will hand that out to me. If I wanted to go something like bedrooms, I will just put that name in here, and you can try this out yourself. So now it's bringing the number of bedrooms, right? So you can address, you can find a column by the labeled index here or by the actual numerical index as well. Either one is fine. What we use data frames for a lot of times is like, you know, when you go to a spreadsheet and you're trying to manipulate it and you're like, well, I want this column here and I want this column here and I want this column here. And what do? Create a copy of the spreadsheet? Do you hide the other ones? You delete the other ones? It's a bit of a pain. In a data frame, you just specify what you want and you can do it in context, meaning it will actually create a new data frame for you. And now this new data frame only has it has, of course, its index. And again, the index by default is numerical index, but this only has 2 columns. It has address and price. So I've actually sliced my data frame into just getting 2 out of the 5 columns from that. Very, very common thing to do, because let's say you got non-numerical data and numerical data in your data frame, you would slice out the non-numerical data frame and do things like one-hot encoding, which we'll talk about later, to convert that into numerical data. So very, very common thing to do is slice data. And you can also do location-based access as well, which is very important. So if I wanted to figure out, well, okay, what's in what's the second row of my data frame, or what's the third row, I would use this lock and iLock, just like we use it in series, but this time I'm actually accessing a data frame, right? And you can see here when I mouse over that data frame, it's got 5 columns, 5 rows. As always, these notebooks are very verbose, because what I want you to do is go through these notebooks by yourself, read what I wrote here. So I'm not going to read off verbatim what I'm saying here, and I want to show you by example. So you can read, you can see yourself what it's doing, and then just read what I'm writing in the notebook to kind of understand. In place equals true. It's a way of saving memory in your code file, because it's saying I'm manipulating this data frame. Let's say I want to slice the data frame. I might want to assign that data frame to a new data frame so I still keep my old data frame, right? So now I got 2 data frames. I'm assigning this data frame, this 2-column data frame, to something called address price data frame. And that is a data frame with 2 rows. Well, I'm actually not sure. It's got 5 rows and 2 columns, but I still have this one here. I haven't manipulated this, because sometimes you want to keep your original data frame pristine so you can use it for other things. But here, when I say in place equals true, I'm allowing it to change the data frame. So now when I print out this data frame, my index is actually, I've changed my index from a numerical index to an address-based index. So now what I can do is using my label-based index, I can look up by address. Maybe if I ever had a customer ID, I could switch the index to customer ID. And of course, slicing is one thing, because it's one thing to slice by columns, but what if I want to slice by columns and rows, or just by rows, right? Pretty common. And what am I, the other question is, what am I slicing on? And to do that, again, remember we talked last week about operators and compound operators. So for the most part, we're using operators. A lot of operators will use our numerical operators, but of course you can also use string operators as well if you want to search by a string value. And here again, you see the power of data frames, because instead of having to write a formula in a spreadsheet, I'm basically saying for the data frame, for the price column within this data frame, give me back any houses that are greater than 56,000. And remember, most of the operations and the functions within Python and other languages are Boolean operations. So it's not actually bringing you back those explicit values. It's telling you if a given address is true or false. And then if you want to find out the actual values, you can do something like I'm doing here for printing that filter data frame. because here I'm just printing it out. It's giving back true or false. You can see here it's true or false, but yet what I'm doing here is I'm asking for bedrooms are greater than 1, and I'm inserting that into another data frame. So this is a very little nuance here. I should note that. Notice the second data frame, are nested. So you're taking that data frame, and that's a filter. And just imagine like it's a filter like you would here, or a filter like you would here. You're filtering, but you're using that data frame to filter to return back a set of true false values on whether that value is greater than 56,000. And because you're putting that into the data frame again, it's going through all those rows in the data frame and saying, okay, print this value if true. And the only value it's printing if true is these ones here. Even though 45,000 is less than, oh, it's saying greater than 1. Okay. Sorry, it's using this filter here, not that filter. So it's saying if the number of bedrooms is greater than 1. So if I said that was greater than 4, there's only one house with greater than 4 bedrooms. Yeah. So do note that that can be a little, you can skip over that very quickly. Notice the, sorry, I think a few people, so tell me if you can see that example. And so let's see what we left to do here. One very important data frame here. Sorry, another very important one, which we covered in our data literacy, is the describe. So when we talk about data profiling, one of the key methods for doing that is the describe method. And the describe method is pretty cool because it gives what we call summary statistics around a given data frame. And this is where the data frame comes into its own value straight away, because again, on this spreadsheet here, we have something like 1,464 rows. Yeah, you can go and look at all this data, but there's a lot of data in here. This is actually a very small data set, but it would take you a good 20 or 30 minutes to go through this. And what if you wanted to figure out, well, on a given data set, you know, what's the mean? What's the standard deviation? What's the min, max, all that stuff. So these are all very important values. And I'll get into them in a little more detail when we look at a bigger data set. But these are what we call summary statistics. And quite quickly gives you an idea of what the data, what the distribution of the data is, right? So you can see here, yeah, that's not a very good example, but you see here, the minimum value is 450,000 versus 600,000. So you'd automatically start to see outliers and stuff like that. And here I can see, you know, number of bathrooms. We've got 5 rows. Minimum bathroom is on average is what? Sorry, minimum on average is that the minimum? 1.5 bathrooms. Sorry, I'm getting confused about the number 1.5. Keep forgetting to have half bathrooms in the US. So gives you an idea of your range here. So the minimum is 1.5, the maximum is 3. Maximum number of bedrooms is 4. Minimum is 2. So for example, if you're trying to build a model to model studio apartments, this would be a terrible data set to do it on, because it doesn't have any studio apartments, it doesn't have any 5 bedrooms. So Again, describe can tell you a lot of information about a data set. We'll go into that in more detail. Now, the issue with describe is by default, it only describes numerical data. But a lot of times we want to work on non-numerical data as well, even though machine learning algorithms don't like that or data science algorithms don't like it. And what you do here is you use this parameter called include all. And what it's doing here is providing a different set of summary statistics for non-numerical values. So it might use something like the top, meaning the top value is most of our data set is single family, and maybe the and how frequently that occurs. So single family and occur twice. So again, looking at your data set, like, okay, I got two instances of single family. That's not a good data set to do some modeling on. So that's the end of the first notebook. As usual, we do have exercises because I want you to try this hands-on. Yeah, sorry. Let me see if, okay, sorry. Hopefully that font size's big enough. But we do have a set of exercises with solutions. So much like last week, don't forget, don't cheat yourself. Try these exercises out. It'll be well worth the effort. So we've got one exercise on series and one on data frames. So let me see what other questions I have here. Yeah, so I see a question there around list and data frame. So again, to use list is built in. List is built-in structure to Python, like it's default out of the box. It's basically, let me see here, I'll show you. It's kind of like one dimensional, right? Like if you're building a list here, this is a list. It's very much one dimensional, and you would use this for a small amount of information, right? A data frame, which we'll continue to look at more examples, is much more sophisticated. You would use that for much larger sets of data. I would say, yeah, so again, data frame being two-dimensional, x-axis, y-axis, rows and columns. That's a couple of key important points there. Why would you use, yeah, another issue with lists is, I don't know, labeling it's kind of like not the best. So it's pretty much a low format here. Series is something that's got more, yeah, so let me see here. So better off to show you what I mean here. So if you look at a series here, so that's a pandas series. You've got a lot more functions you can manipulate against it. So a lot of times with these things, what's the difference as well? The difference is all the functions you can apply around that, right? So a lot of mathematical functions here. You might want to print out the head of it, like the top number of rows, the bottom number of rows, and you can do all of this in data frame, by the way, as well. So that can be useful. See here, group by, history, first value, fill NA means fill any blank rows, filter, things like that. So if you've got a very small set of data, you want to use a list. If you got a larger set of data, a series is good. And then if you got a very large amount of data, then use a data frame. Is always a good one as well. So we can come back to that. But again, it comes down to which is the more powerful, because I think it'll become clear why data frames are my preferred data structure over, say, a list in the series once you can see all the functionality in it, because a series does have a lot of functionality and some of it's duplicated, but a data frame kind of builds upon a list. Sorry, a data frame builds upon a series, and a series builds upon a list. So think of the hierarchy of data frame as the highest hierarchy, then series, and then list. And everything you can do in a list, you can pretty much do in a data frame, and then plus plus. So let's look at our second notebook, which yes. And now you'll really see the power of a list and a data frame. Sorry, a series and a data frame. What we're going to do in this notebook here is we're going to upload a file, and the file you can upload here is this one here. So you can actually connect your Colab to your own Google Drive if you have one, if you feel comfortable with that. But generally what I like to do is just upload it, right? And again, you can upload a pretty large file here. So to do that, you can go to your go to files within here. So you'll see a little file icon within Google Colab. You can click on it here. This is the file upload icon. I can upload here, and then I see a file here. So that's my Kaggle house price data set, which is the exact same data set as here, the one we've been talking about. And once you've uploaded that to your notebook, which again, you don't have to do right now, move that into whatever directory you may have in Colab. You may have none, you may have one, but just remember Google Colab by default uses this here. I should say that. That's by default, it's going to have that here. And then I have my sample data. And then within here, I'm going to, actually, that's the wrong data sets because that doesn't have the right name, does it? Yeah. So let me go and upload my file I need. I need a Kaggle house price data set. I ran this before just to make sure it was working. So what I'm going to do is, while that's loading, I want to clear all my outputs. So here's my house Kaggle data set. I'm moving to my sample data directory, and now it should be able to load it. So what I'm doing here is giving it a local file path. Again, this is Colab because it's in context. I have my sample directory, and that's the name of the data set. And what I'm doing here is taking my pandas data frame using the read CSV method and giving it that CSV file I uploaded. And then remember in series, we printed out the header, the tail, exact same function. I'm basically saying, give me the top 20 rows to make sure I've loaded it in. So this is going to take a little second to run. And what it's done here is it's printing out the top 20 rows. So from 0 to 90, it's printing out. It's not showing me all 80 or 81 columns because that's too much data. So what it instead is doing, it's shortcutting it using the backslash, which we can talk about later. So now within my data frame, I have a representation of my spreadsheet data here, and that's pretty awesome. First time I did this, it was definitely a hallelujah moment. That was pretty cool. Come back to me. And now we can do all kinds of manipulations on this. So let's start here. So another thing we can do as well is let's say it was a file on stored somewhere on the internet, right? You can actually use another method called wget. So if I go to this file on the internet, you guys can actually see this as well. Someone's asking, is the data frame structure? I'm not sure. I actually, Python is, sorry, Pandas is open source. You can go look at the code or ask Perplexity or Anthropic. I don't believe it's stored in a dictionary under the hood because I believe it uses a more efficient data structure than a dictionary. So it's not just one big giant dictionary. If you're asking how it's actually built under the hood, I don't believe it's built using data dictionaries. However, you can use data dictionaries to build a data frame, but it's not like it's taking a data dictionary. It's taking the representation of the data in data dictionary, storing that in memory, and then using its own representation to access that data. So again, I don't believe it's built on top of a data dictionary. That wouldn't be, because pandas is meant to be, like, again, why would you put some data in a series or a list? Because after a while, after a certain amount of data, those data structures become very unwieldy and they're slow. Whereas pandas, it's not meant for huge data sets. For that, might want to use something like Polars, POLARS. NVIDIA supports that open source project. You might want to use something more sophisticated like PyArrow. But pandas, when it was built, 15 years ago or 12 years ago, was built with scale and speed in mind. But you can actually store a data dictionary in that. And does it correspond to the data dictionary structure? No. So again, just to remind you here, a data dictionary has key value pairs. So you can look up a data dictionary by a key and a value, but you have one key and one value per row. Whereas a data frame is a much more sophisticated structure. You can still use key value pair lookup by, say, using an index or location, but it's a much more sophisticated structure. So you can use elements of that. So if you go through that first notebook I did slower than I did, it'll come to you. It'll make sense. But we've still a bunch more to explore of the pandas data frame. So you're still learning the data frame, and you'll see again some more powerful functions you can do there. So what we're trying to do right now is load in a real world data set into the data frame. And another way of doing that is, so this is a file in one of our repos on the web, and you can see it's got the same data, but very unorganized because all is a bunch of comma delimited data, hard for us, a human, to read. But using the wget method, which is getting something over the web, we can actually load that right in. So there's a bunch of data sets you can play around with on the web that you can grab using this way, right? So, basically scraping data off the web. So here what we're doing is we're getting the file from the internet, putting it into a CSV file, and then loading that CSV file into our data frame. So here now we're creating a second data frame based on that value from the web here. So you can see here again, I'm printing it out, all the responses. So that's great. So now we got a data set that's a real data set we can play around with. And remember we talked about the describe, and that toy function wasn't very interesting. Now we get into something much more interesting. Here we're using describe. I want to get the summary statistics, but I want to get it on all columns, right? So numerical and non-numerical. And we're also printing out the sales price, because remember the thing we want to predict when we talked last Tuesday about the feature, the target feature, which is sales price. Want to make sure we have sales price, and you can see that here. And what we're doing here is we have various, like, let's see here. Here's zoning, and again, like, I don't know what MS zoning means. I think it's something to do with zoning laws, and I can see I got 1,460 entries for zoning. There's 5 unique values, of which there's a bunch of, the top value is RL, and R of RL zoning, 1,151 are RL zoning. And this is why describe is so powerful, because I have no idea what RL means. But if I was to use my brain and say, okay, this is mostly housing, that must mean something to do with R, maybe stands for residential, right? So I would go and research that and maybe look up a cheat sheet that would tell me that. But I'm seeing lots of information here. So see here with alley, like, what does alley mean? Does the house have an alley? Well, if it's a house is in the suburbs, it probably doesn't have an alley. So of the 1,460 entries, only 91 have an alley. So that's not a very good set of data. Pool. We've only got 7 pools. We've only got houses with 7 pools. 281 rows have fences. So now you can see, without actually looking at the spreadsheet and trying to do one of these. Again, this is why data profiling, data analysis is so important. Like, you could look at a spreadsheet and go blind. Like what am I looking at here? You know, if I froze my first row view, even if I freeze my first row, you know, NA, no pools, how many pools do I have here? Like, it's very confusing to look at any kind of solid data set. And using that describe function, I'm able to get a whole lot of information out of this. I can tell that if I was using this data set to try and predict the value of a house with a pool, it's going to do a very poor job because only 7 houses have pools, right? So pool is an outlier. And so, yeah, can't stress that enough, how important that is. And the other thing is like sales price. Remember, sales price is the label value in supervised learning. This is the thing we're trying to predict. If we don't have a sales price, if we're missing a sales price, then we're not in good shape. And I can see, I know there's 1,461 rows in this data set, but row number 1 is the header row. So I'm not missing any sales price, which is good. So again, super, super important. And now let's kind of do something a little more fun. So I don't know if you guys have been keeping an eye on the stock market, but it's been pretty interesting. You can actually use Python to go out and scrape the web view. So pull data into a data frame. So here where it could be some website, you can use this library called requests, and then to scrape that data, we'll use another library called Beautiful Soup. Great name. So we give it a URL here. We get the response, and then we print out that value here. So you can actually go to example.txt, as I am here. And you're like, why would someone have a website like this? Well, it is what it is. And I can go right click and I can inspect this. Yeah, so I think you heard me when I said I can go to any website. Here's an example website and inspect the website. I can go look at where all the tags are. I don't know why my microphone's so sensitive. I'm moving it a little closer to myself. So I can look at all the tags, and I can basically programmatically pull in that website by saying, find me the H1 tags, find me anything with a P tag. And using these methods in Soup, Beautiful Soup, I'm able to find that. So that's how I'm able to print that tag here. And this is very important because a lot of times when we're doing data science and AI, we don't have the information in the company. We don't have ourselves. So we have to go out there, you know, respect the request of the data science of the website. A lot of websites allow you to give you access to their data. Some don't. And here we can go to one of my favorite websites, which is NASDAQ. And what's going on with Apple today? Apple is down. Sorry for all you Apple stockholders, myself included. Could be a good buy to dip, right? No investment advice offered. Hopefully none taken, but you do your own judgment here. But let's say you wanted to build one of these agentic AI workflows, and you wanted to every time Apple raised 10%, you want to go out and treat yourself to an ice cream or something, whatever you want to do. Or when it dips 10% or 20%, you want to go and buy that stock. Well, now you can. So what you can do here is you can go with the exact same request, give it the Google price, right? Apple, and what's the price of Apple right now? It's 173, and wow. Is it really down that far? That cannot be right. Oh, sorry. I was looking at this. I was panicking there. I was looking at the 6-month trend. It's down 4 or 5%, which is not great. But again, Yahoo Finance is a very friendly website, a great website if you're interested in finance, by the way. So what I can do here is go to that page. I'm sure you've all seen this error message. I can check for status code 200, make sure the page is live, and then I can parse it. And then what I'm doing here is the exact same thing. What I'm doing here is I'm looking for that price. So I go here and I inspect, and I notice that the price, come on, price, is covered by this tag called JSNAME. Don't worry what it means. It doesn't matter what it means. Sorry, the class is, it's got this double bar class here, and there's the price, right? So again, with Beautiful Soup, and if you understand HTML, I just need to look for these two here. So, and that's what I'm about to do. And let's see if it still works, because see the two classes I have here. And yeah, it works. So I'm saying based on this class. So basically you can find any information in the website as long as you can inspect it. It allows you to do it, and that's the price here. Let's see our second favorite stock here, NVIDIA, NVDA, which everyone was freaking out about. What's NVIDIA at? NVIDIA is at $97. So it recovered a little bit from yesterday. That's good news for all you NVIDIA stockholders out there. All right. So, and again, I go through in detail how you do this. So go through this yourself slowly. But I often scrape data sets from Wikipedia and other data set providers that provide, and this is how you can get large chunks of data into your own environment. So this is very important. Another way of accessing data, and again, where's that data go to? That data goes to a data frame. Another way to get data is through an API. So here, for example, is a simple API you can play around with. Sorry, why isn't it letting me do that? So, I'm using the long API here. So you can take this API here, and you can go to it, and it's going to feed you some data, right? That's item 1 in the API. Here's item 2. Here's item 3. I think it's only got 3 or 4 items. So again, if you've never used an API before, this is a great example. And what we're doing here is we're just pulling in the API data, and see here, pull in the data, right? And again, now we could pop that data into a data frame. It's ordered. So very, very important technique for getting data. So you don't want to be creating these little simple data sets in a list and a series. You want to get the data from someplace, a file, an API, a database, put it into a data frame or a similar structure, right? So that's how you get data. And again, this is our second thing, like where do you source data is a big part of that. All right, so let's go to the third notebook. Now you have the data, and remember, data from the web, data from the web, data you pull in from various places. That's not going to be very clean data. That's going to have missing data. That's the number one thing we kind of have to fight against is missing data. And then we have to figure out, well, how important is that missing data? Do we fill it in? Do we backfill it? So how do we find we have missing data? So let's go to our house price Kaggle set again, and we're going to pull it from the web, directly from the web. We're going to read that in, run this notebook. We might get a notice that we've got too many notebooks running. So again, we have the data, and I'm printing out a little bit of it here so we can see we have it. And the first thing is that there's a couple of functions we can look is, and the great thing about Python is a lot of languages don't allow you to do this, but I can take a function, say is null. So that returns back is null returns back if the value is null or not, right? But the problem with this is it's going to give you every single value in your entire data set, right? And it's going to give you back Boolean values, true or false. So when you do, when you add in sum on it, what it's actually doing is counting up the trues and ignoring the falses. So let's run that. And here's the link to the third notebook. So that is, that can give me a sum of missing values, right? So come on. So it's showing me that I got about 56 missing values here or something like that. And now what I can do is I can print off the missing values. And you can see what I'm doing here is a simple for loop, and I'm basically taking the columns with missing values here. So I'm filtering in my data frame and saying, give me the columns, only the columns with missing values. And then I'm using a nested structure again to go through and saying column whatever has missing values here. So this is how I get to this here. So I'm saying column lot frontage has 259 missing values. Alley is 1,339. So all of those are columns with missing values. And what do I care about? Do I care about a fireplace? A lot of modern houses don't have a fireplace. I probably care about a garage. Like if the house is a suburban house and it doesn't have a garage, is it a missing value, or we just forgot to collect it? Or maybe the house doesn't have a garage. So I would be worried about that. I'd probably be worried about, again, if this suburban house doesn't have a basement, is it missing or something like that? Lot frontage is very, very important, because usually a lot has, like imagine a house is on a square lot or a rectangular lot. It's like, is it a very narrow and long house, or it's got a good lot frontage? Because generally speaking, houses with, imagine picture a beautiful house. It's got a big, beautiful vista of the house itself, well manicured, and what you're envisioning is a long lot frontage. So if I'm missing that, maybe it's an apartment building and it doesn't have a lot frontage, but I would investigate that. If I'm selling condos in the city and there's an alley behind me, probably want to know that. Because a lot of places you need an alley. That's where you put out your garbage and stuff like that, right? So this is very important, and very, using our for loops, we're able to loop through this and find it out. And then what we're doing is, okay, so what I'm going to do here, one solution is, if the row is missing values, just get rid of it. So what we've done here is basically taken our data frame and dropped rows here. See the way that's 1,460 and 81. And now this data frame has 81 columns with no values. I guess that was after we fixed the values here. So anyway, you can create so one option is, if you're missing values, is drop them. This line of code here you can kind of ignore, because it's not doing quite what I envisioned. So a lot of times, but that's a very harsh response, right? Because just because a column is missing 259 lot frontage, that's no reason to get rid of 259 data values, because 1,460 is not a very big data set. So we want to keep those. So we can do instead, and again, we talk about this in data literacy, is we can fill it in with something, right? But what are we going to fill it in with, right? So we do what we call a lot of imputation. You're going to impute or generate a number that you're going to put in there. So there's different ways to do this. And first, what we have to do is we have to figure out which columns we want to get there. So here we're doing, again, looking for house data, looking for, again, columns with missing values. And here they are. And we have 19 items, columns before. Then we're saying, what we're doing here is looking only for columns with numerical columns, right? Because we can only, let's say we want to put in the mean or the average value. We can only do that with numerical. So we're saying NP, we're using NumPy here. If this is a numerical value, include it. If not, don't do it. So now you can see that our data set has gone from 81 columns to 38 columns. See here? Because that 38 there, sorry, I'm on a different screen. That 38 here, I can't highlight it and look at the same time. There's only 38 numerical columns in there. The rest are text. So now we went from columns with missing values before. We went from 19 to 3. And so what we're doing here is what we want to do is look at the different values we can fill in on these columns based on different values. So let's take a look at that. So a couple of ways to do this. So I'm just trying to find my place here. Haven't looked at this code in a couple of months. Again, we're looping through this data here. We're looking for the mode or the average value, looking for the most common value, right? So say, for example, I may seem very strange, but remember, you're not going to create a house price listing. So let's say it's missing the number of bedrooms. Why would you, if it's missing number of bedrooms, wouldn't you go back and fix the data? Yeah, that's option number one. But your boss wants to model tomorrow. You're not going to run around for a bunch of houses and look for the number of bedrooms. And you're not actually posting this on the house listing, but it's missing the number of bedrooms. And you see that on average, if you have to put a floor value on it, the average number of bedrooms in your data set is 2. You can maybe do something more sophisticated and say for a house this size and for the number of bathrooms, how many bedrooms there is. But for simplicity's sake, just imagine you're taking the most frequent value, right? The mode. And what you're doing is you can use this for both numerical and non-numerical values. It could be like, what's the most common house color on the block? It's white, if that was a thing. So just put down white. And again, because you're using it in the model, yeah, it'll skew your model a little bit, but it's probably better to have a value than have no value. If you're doing that a lot, it could cause problems. But again, I'm kind of getting ahead of myself. Like understanding how to do that and not how to do that is a little bit more of an advanced topic, which we'll talk about in our machine learning and modeling. But again, just assume that you don't want to delete the values. You just want to impute values and you want to fill them in. So again, using dot notation, nesting that here, what you can do is get the most average value, the most common value. And then what you do is you're filling. So anywhere where it's got a missing value, NA, not available, fill NA. So what you're doing here is you're taking the most common value, and in that same data frame, you're putting this in here. So again, if this is going through a little fast, just study this set of code here, but you're filling in missing values. Very, very important here. And here we're just collecting the value. So let's see what that'll look like. And here we're, I don't know, this is 0, but we're guessing the garage year built was 2005 because that's the most common value. And all those lot frontages we're missing, we're giving it a lot frontage of 60. So again, it may actually not be, if there is a house that has a lot frontage, it may not be the actual value, but it's just something that you can give your model so it's not worried about missing values. Another thing we deal with, which we talked about in our data centric, is dealing with outliers, right? Plotting outliers is a really cool way to deal with this. So this is a box plot, which I know a lot of people, especially if you haven't been in finance, you might not be familiar with this. But let's say we're dealing with sales price and want to know if we've got any outlier sales price. So here, the way you read a box plot is the vast majority of the range and distribution occurs between $150,000 and $220,000. Then you start to notice some outliers here. And then you get 2 big outliers here. So you have 2 house prices that are more than $800,000. And again, I'm just showing you code here, so I won't get into the details again of why you want to do that. But a couple of ways to deal with this. You can remove the outliers, or you can use various techniques. And here we're using, looking at our pretty common IQR technique. Well, to calculate an IQR, you take the third quartile, subtract the first, and use this little formula here, and it gives you kind of a nicer range to work with. And if I plot that out now with that new range, and again, there's lots of different techniques you can use here, but that's just one. And now see how the prices have gone from whatever it was, this distribution here, to a bigger distribution, which is probably better for modeling. And we still have some outliers, but now they're in the 350 to whatever range. So So there's lots of different ways of dealing with outliers and determining what is an outlier, because don't use something suggestively. You usually want to use a formula like the interquartile range here. And as the name suggests, it uses quartiles to figure out what the range is here. And I know this sounds strange, but again, what you're doing here is you're trying to build a model. You're not throwing them out and saying, we'll never use this house prices again. You're just trying to build something that'll be reflective in a range. Another big problem you have is duplicates, right? A lot of data sets contain duplicates, and if you have duplicates in your data, that's bad, because now you have more instances of the same data, and that will skew your model results. So to get rid of duplicates, pretty easy. Here, what we've done is using the head, I've added 5 new. So here was our, I've added 5 new rows to our data frame. So see, it was 1,460 rows. Now it's 1,004. No, sorry, that's 5 new rows, and then I added that one in here. So now our house data's got 1,000. Sorry, where the hell did I do this? Finally, oh my God. Oh, I've already run the code. Sorry. Can't tell me, because when I added it and removed it, I'm like, why is it showing me 1,406? The row count after duplication is 1,465. And then I went and I took it out again. So I dropped the duplicates. So again, going through this slowly, we're creating 5 new rows. Then we're using the concat function, just like you would use in SQL. We're concatenating 5 new rows into the data frame to come up with a new set of 1,465. And then what we're doing is find the duplicates. So we're using the duplicated function to say for a house data frame, finding duplicates. And look, it's not looking at one cell of data or one variable. It's looking across an entire 81 fields, 81 field values, which is pretty handy, because you know, imagine if you're trying to find duplicates in this data set here. You know, you'd have to write a function for that or use the duplicate function, but not trivial. And like everything else, data frames make it trivial. Another issue you would have, we talked about in data literacy, is addressing data inconsistencies, right? So imagine you're working with European and US data. One is using square feet and the other one's using square meters. You have different kind of address formats. Let's say I'm doing a search by lowercase, and some house prices have addresses, or some are uppercase, some are lowercase, and things like that. So here what we're trying to do is standardize values. So we're doing things like moving values to lowercase, or moving stuff to uppercase title values. And again, with a data frame, you can apply that one function across everything. So again, pretty useful. What I'm doing here is finding the most common value, and then standardizing those values here. So it's important to know what's the most common value in any given for any given feature, and then I'm just manipulating those other values. Sorry, I just want to check the time here. We still have about an hour left, or a little less. So you'll often see as well in a data set, you'll get talking about data types, which we discussed at the very start. Maybe you're expecting numerical value, and that numerical value is actually stored as a string. And in that case, you want to check what the type is. So here, for example, is we're checking is bedroom above ground an integer type, and we're forcing it to be an integer type, right? Because we want bedrooms to be, you know, because it's a count, right? So we want that. So we can use this here to force it to be bedrooms above ground. Here in sales price, same with sales price, we want that to be numerical. So if I didn't have this here, would it cause an error? Let me see if it'll cause an error. No, it doesn't cause an error, but sometimes you have to use a course. As the name suggests, you're forcing it to become a numerical value. So here, using the you can look at the data types here. See, the data type is now integer 64 for the for both of these. Like, you might want it to be a float, right? I don't need decimal places for house prices, but a lot of times you want to work with consistent data and across data type. Common values, we kind of looked at that. The mode here we're actually using, instead of using a for loop and looking for the mode, we're just getting unique values. And we can also use the is in for understanding if it contains a certain value, right? So let's say this is how we do data validation. So we're looking at our data set here, and we expect certain townhouses because we know there's only 5 values, a certain type of house we want to be looking at. I don't know where that is here. Yeah, building type. We know there's only a certain amount of values, but you can use validation here and say, okay, I'm expecting 1 family, 2 family, duplex, stuff like that. So if I don't find that, it's not a valid house type. All right, so that's the end of notebook 3. Any questions? Any more questions on that? And again, guys, I know we're going through this quite fast, but again, study these notebooks in your own time. Go through the examples yourself, and definitely try the exercises. So let's move on to notebook 4. So when you have a free version of Google Labs like I have, it's going to ask you too many sessions. Don't forget about it. Just remove the old running sessions and focus on the one now. So let me get rid of this code here, this outputs rather, and run all of this. No, not run all of it. So in this one here, we're going to be looking at reshaping data. So reshaping data is something we do quite common because, okay, I got too much data in here. I can't read this data. I wanted to group this data. I want to summarize it. I want to know how many of various types we have in here. So shaping data, or I might want to pivot data, right? It's something we do quite often in this. Let me just close down this tab here. And let me give you notebook 4. And yeah, quite a bit of preamble here why we want to do it. Data comes in different shapes and formats. Like I said before, different data types, maybe an unexpected data type. If you want to do machine learning modeling on that, if you want to even do visualization, right? So certain people always forget this, but certain visualizations you can't do a line graph on non-numerical data. And let's say you want to create a line graph on your non-numerical data. How would you do that? There's ways of doing that. Feature engineering, which we talked about last week and we'll talk about on Thursday. We need to shape our data for that. We want to normalize our data. We want our data to be standards with consistent scales. Here's a very common problem. So let's say you've got 2 sets of data. One is number of bedrooms, which goes from a scale from maybe 1 to, I don't know, what's a big size house, 6 or 7 bedrooms. That's a scale of 1 to 6. And then let's say you're dealing with luxury Manhattan real estate. That is a scale of 3 million to 300 million or whatever. I don't know what the most expensive skyscraper I think was apartment was, like maybe 150 million, which boggles the mind. But think about the scale in that. Like one scale is down here and another one is up in the stratosphere. And we can actually do, when you want to rescale those, you could say, well, okay, let's say we want to scale number of bedrooms between a value of buckets of 1 and 10, bucket 1, bucket 2. And you can actually do the same with real estate prices. Instead of going from whatever it was, 3 million to 150 million, you could say what's in bucket 1, everything from 3 million to 10 million, and bucket 2 is 10 to 30 and 30 to 40. So see what I mean? So you're able to rescale things is very important, and normalization is very important. Aggregating data like means, averages, also very important. Data reduction. If you remember your principal component analysis, where you reduce a set of data down to a reduced, more salient data set without losing any of the data's features, such as its distribution, its standard deviation, and all that kind of stuff. And then, of course, you want to be merging data. You could have data from two different data sets. And then you want to do encoding. Not indocking. I don't know what indocking is. Encoding is where machine learning models require numerical versus non-numerical data. So I can talk a little bit about encoding because I've mentioned it a few times. These slides here. There is a couple of slides I skipped because I want to focus on the code. Again, think about numerical, non-numerical, categorical, qualitative versus quantitative. So what we often want to do is encode data for representation. So imagine you got a set of colors. You can encode them as, because you got 5 colors here, encode them from 0 through 4. That's a way of doing encoding. And sometimes they're ordinal meaning they have an order. And one-way machines, a very simple way to get non-numerical data into numerical data is to do something we call one-hot encoding. So bear with me. This seems like a little confusing, but imagine you had 3 colors, right? Just 3 colors. Because there's 3 colors, we can encode that in a vector or a list or an array, whatever you want to call it, of 3 values. So red is encoded as 1, 0, 0. So the first one's flipped on. Green is 0, 1, 0. Yellow is 0, 0, 1, right? So you can see it here in this matrix here, 0, 1, 0. So when I go green again, well, green was already 1, so now this is 1 here. So this is an example of one-hot encoding, and you can identify unique, because all of these are unique, right? Yeah, unique categorical variable, and for each unique category, create a new column in the data set. And this works extremely well. You might ask, well, what if I had 1,000,000 features? What's stopping you? If it has 1,000,000 features, then you have 1,000,000 columns, and that's fine. It'll be very, very sparse. You'll have 1, 1, and 900,999 zeros, right? Sparse encoding, not very, very memory efficient, and there's dense encoding that uses numerical values, which we'll talk about later. But this is a very simple technique that's quite key. So yeah, so look at that, and the slides will be included, by the way. So we're going to show you how to do that coding here. So I'm going to go through these examples pretty quickly because, data conversion is a little boring. Hate to say it, but it is. Here we're doing is we're converting integer values to float values, because let's say you're doing financial calculations and you want it to be 2 decimal places. Very easy to do numerical, come on here. So see the way these are integer types, int64, and now they are float values here. So now the data type was 64. Now the type is float 64-bit float. Another, yeah, here's some more examples, like some real examples. So here, see here, these are all kind of non-numerical. We want to be numerical. Here we're doing something interesting. We're doing mapping. So we're using our dictionary to say if it's a value of 1, map it to 1, value of 2, map it to 2. And then we're using the map function to actually run that. And another thing we can do is just replace. So here what we're doing is, again, nested dot notation. We're saying, okay, for price, first find and replace the dollar value, then find and replace the commas, because in numerical values, a float value or integer does not hold a column. So here we see we had it printed out, and now we have these converted into numerical values. So very, very important. And again, a lot of time when you're working with data, you're looking for stuff like this. If you expect to get an average of a value, make sure it doesn't have a comma or a dollar sign in it, because certain code that'll break. Time conversions are also very common. It drives me crazy. Like, everyone's got a different standard, time standard. Different companies got different times. It's worse than meters and meters and feet. Like, all different kinds of time standards. And so you want to force that into a different kind of standard here. So you can use pandas to date time to enforce certain values on that. And here you can see these were brought in as an object, because in Python by default, in a lot of languages, this would be a string, but it actually treats it as an object, right? And see how the year built was an object. And once we said for the year built column, convert it to date time using this format, right? And you can see here, see the way these dates were like 2005-08. We're actually able to give it a value as well, like the last day or the first day. Another interesting thing you might have done in a spreadsheet, which used to be quite difficult to do, is to pivot data, right? So pivoting is basically where your Y column values become, your rows become columns and your columns become rows, depending on which way you want to pivot. You want to pivot plus 90 or minus 90, but columns can become rows and rows can become columns. So let's say your boss comes to you and says, well, okay, give me the average price by number of bedrooms. So what's the average price and other information by a 3 versus 4. So what you do is you would pivot. So instead of like number of bedrooms being a column, you want number of bedrooms to be a row almost, or something like that. And then on your columns, you could say, well, bedrooms, like for each, how many 3-bedroom house do I have? What's all their information, stuff like that. So maybe the way to do this would be to actually just print it. So here we have this dictionary. We're creating a data frame, and you can see here I basically said the columns become bedrooms and the values become price. So now I can figure out what's the average, like which of the 2 bedrooms we have, which have a price, of the 3 bedrooms, which we have a price. And we see we have prices mostly for 3 bedrooms in our data set. We only have 1 of 2 bedrooms and 1 of 4 bedrooms, which is very, very useful. Because again, if I wanted to just price 3 bedrooms house, like the average area, the average price, build a set on that, which is quite useful. Okay. So another weird thing you only hear with Python, because I never heard of this when I was programming R and JavaScript and Java, it's called melting. So to melt data, we want to transform from a wide format to and this never made sense to me, going from a wide format to a long format, because they're both wide to me. They're both long. Like, I always think long, length, X value, horizontal axis as opposed to the vertical axis, Y values. But it's kind of like pivoting, converting columns into rows. And I have this melt function, which you can play around with here. But again, very useful, because say, for example, you wanted to visualize this and you wanted to do a time series from various dates. Now, because you have the year, because you converted the year into its own set of rows here, and then you have a price on it, you'll be able to see what the price is doing over time. So melding is does have its uses, especially when you're trying to visualize something and stuff like that. And then another favorite feature we use a lot is min-max scaling. So this is like a little it's amazingly simple, but it's like almost like a magic trick. right? So what you want to do is, as I talked about before, you have a range of data, but you don't want to use that actual range because the range might skew some of your modeling here. So basically, we're taking something like what we're doing is we're taking all these values and we're doing min-max scaling. So min-max scaling is a very, because I've used this myself in a lot of different projects. And what you're doing is you're taking the you're taking the max from the minimum and scaling it based on that, right? And what you're doing here is you can see how it's scaling it across the data frame here. And again, this is doing it. What's magic about data frames is doing it across the entire data frame. So it's taking that, whatever the value is, and then taking the difference between the max and the minimum, right? And it does that in every single feature. So you can see here, we're going from, and see how it preserves the data. So number of bedrooms. So the house with the most number of bedrooms was index 1, right? See index 1? And the value of 1, the highest value between 0 and 1 is this one here, right? And then you get a bunch of 3s, and then you have a 2. And the 2 is the lowest value. So that's the lowest value. So even though you have no idea the number of bedrooms now, you still know that this one here had the most number of bedrooms. The least number of bedrooms. This one had the most. And it's amazing, but in a lot of cases, that's the only information that the machine learning model or the AI needs. The AI is not sentient. It doesn't know what a bedroom is. It doesn't know what 3 bedrooms mean in that context. All it cares about is the numerical representation and the pattern of that. Because if I give it these values here, it would figure out based on the data that this was the most number of bedrooms and this was the least number of, this was the least number, right? And it has the exact, we've preserved that information even though we scaled it to a different value here. Same with here, see number of bathrooms, 3 has 3 bathrooms and that's got a value of 1. And this one here is 1.5, 2 has 1.5 bathroom, right? And the same with area, like this one has an area of 2,000 and this is a value of 1. So very, very powerful, very, very powerful thing there. Simon actually gave a good example there about melding data. Yeah, that's a good example, Simon. So scaling these is, and that's just one type of doing it, but it's very, very useful. You can always use standard deviation. Take away the mean for each value, take away the mean and divide it by the standard deviation. Super little simple thing here is to style a data frame if you want to make it pretty. I'm not going to dwell on that. Handling categorical variables. So this is what we talked about our one-hot encoding, which is very, very important. So here what we're doing is figuring out what are categorical variables. For example, dwelling type right here, single family, all that kind of stuff. We're going to convert that to a, we can convert that to a numerical representation. Or in this case, what we're doing here is we're doing something simpler. We're just converting it to categorical. So if it's categorical, so it's still non-numerical, but we can do things such as order it and group it and stuff like that. So here we're saying dwelling type, and dwelling type is an object, but now we convert this dwelling type to a category, and now it has a data type of category, right? And that can be important. So for example, dwelling condition was also an object. We converted that to a category, and now we can actually sort on, see we can sort values by dwelling condition. And it knows to start from, I know we can reverse this, but it can go from a categorical representation from one end of the spectrum to the other, right? So here it knows to sort this by poor, fair, good, excellent, right? So, you know, A lot of values don't have, are not categorical, like flavors of ice cream. You may have a favorite one, but you can't order it. But education is like going from, K through 12, and then undergraduate, graduate, doctorate, postdoctorate, and stuff like that. And you can find out if something's a category by using it as type. So that's great. But again, machines like numerical values. So what we want to do is just do some one-hot encoding. So convert those categorical or non-numerical variables, whichever it is, into a different value. So let's take a look at our data. We have all of these different types of objects, which are basically, for the most part, string type. And this is these are the unique values in each one. So we have zoning, we have street type, alley. Kind of fun to go through all this stuff. In this. So see all these different types here. What we want to do is figure out which of these we want to convert these into numerical values, and that's a really important point to understand, because what you want to do is convert these into numerical values, but at the same time not lose any values here. And there's different ways to do this. So what we want to use is the one-hot encoding we mentioned before here. So what we're going to do is, just like we did with red, green, yellow, and red, we're going to take these values here and we're going to one-hot encode them. And we use this like very, I don't know, I always find it strange. They call it dummies in pandas. So get dummies converts categorical variables into dummy or indicator variables. And so for each unique value in a category, a new column is created. So this is really, really important. So don't lose me here, because this is very, very important. For each unique value, it creates a new column. And this is very weird, because you may say, well, I've already got 1,460 columns, 461 columns. Why would I need new columns? Well, you need new columns because we're doing this, right? We have 3 values. So let's say you had a column called color. That's one column. Now I need to take that one column and create 3 new columns out of it, right? So I'm going from 1 to 3. And why is that important? Because when I have, why did I get lost here? Where did I go? When I'm here, guess how many columns I'm going to need to represent neighborhood? Actually, that's too many. Street, I'm going to need 2 new columns. Here, I'm going to need 1, 2, 3, 4, 5 new columns, right? I have to create 5 new columns, and that's really kind of key to understand how this works. So when I run this, what I'm going to see here is, did I run it yet? Yeah, I did. I didn't. So this is a little hard to follow because there's so many here. What it does is it takes it takes a column. So see zoning, right? Zoning's got 1, 2, 3, 4, 5. There's 5 different zoning types. Let's see if we can find zoning here. 1, 2, 3, 4, 5. And see the values here. So it creates a new column called MS zoning underscore RL underscore RM, so on and so forth, right? And now it's created this one-hot encoding of trues and false, ones and zeros, right? Ones and zeros, ones and zeros, ones and zeros. So true, false, true, false. And you can see here it's doing that representation. And so everything in the data set is either FZ zoning or it's not. And again, for the most part, depending on the number of values, let's say we had two values that were FZ zoning positive. They were actually that. They'll be true. and the rest will be false. So everything, there might be some columns with the value set to 1 or true, and everything else will be set to false. So this is really, really important. A lot of people kind of glance over this. Number one, to convert those in numerical values, which true and false is, it's Boolean operators. Computer can understand that. Depending on the number of values, unique values you have. See all these neighborhoods we had? These are all like, is it in the Gilbert neighborhood? Is it not the Gilbert neighborhood? Super simple, but this is the kind of data you want your model to run on. So very, very important. So we've converted all that data into one-hot encoding. So is it possible to explain? Okay, so standardization versus normalization. Yeah, so a couple of things on that. One is if you look up this data literacy course here, don't know where it went. If you look at this here, I covered it a little bit in here. So if and then in the primer boot camps, we'll have a more detailed explanation of standardization and normalization. Where is it here? It's somewhere here in our statistical literacy, somewhere around here. But in summary, it'll become more obvious when we look at our data distribution here. But standardization usually, but not always, means I'm sure you've heard of the Z-score. Z-score is a pretty common metric used in. How do I get rid of this? Z-score is a pretty common metric used. It's a standard score. Think about standard normal, and what you're trying to do there is standardize around the mean. And for standard normal, you're usually talking about a mean of 0 and a standard deviation of 1, right? So you have this. You have a shape like this. It's not left skewed. It's not right skewed. So you're talking about standardization. Think, score, normalizing around score. So if I wanted to standardize something, I want to standardize it around this, right? So forget about one bedroom and 10 bedrooms, or $10 and $1 million. You're just standardizing around this, and that retains a lot of the shape, right? So that's why standardization works. It usually follows what they call standard normal or Gaussian. Is another term you might have heard, and it's kind of useful because it doesn't lock the data in between the value of 0 and 1. So if you have a lot of outliers and you don't want to get rid of them and you want to keep them, it does a good job of preserving those. Normalization, on the other hand, and I showed you an example earlier. That's where remember I was doing number of batches. It's preserving the value between 0 and 1. Doesn't matter how wide the distribution is. It's between 0 and 1. It's not giving you a distribution. It's just well, it's kind of, but it's preserving between 0 and 1, and that is if you want to bound something by if you look at here, you're binding stuff by a range. Within a certain range, that's kind of useful. So normalization, which one works better? It's very, I guess I should know that. I would say for like a lot of the data we're working with in here, normalization would work very fine, especially because again, I mentioned earlier, like a lot of times I use min-max scaling or something similar to like that. That would work fairly well if you got a much wider distribution, more complex data, maybe it's non-linear, some stuff like that. Maybe standardization may work, or a different kind of distribution, because you don't necessarily have to use that one. But generally speaking, standardization kind of gets complicated. But in simplicity, when people talk about standardization, they're talking about Z-score, build something around the distribution about the mean of 0, standard deviation of 1, and Normalization, you're kind of forcing it normally into between 0 and 1. And normalization would be more sensitive to outliers. So you might want to get rid of them. Standardization might not care as much. It depends also the algorithm you want to use them in. Like standardization, the advice you would normally get, even though I don't follow this, is principal component analysis, because the essence of principal component analysis is to standardize your data so you reduce your data set down, but you don't lose the meaning of it. And then logistic regression for sure, standardization, and other techniques. And then normalization, kind of use that a lot in distance-based stuff, and even deep learning, I think, for deep learning models. So again, that's kind of getting a little deep, but think simplistically. When talk about standardization, the mean of 0, standard deviation of 1, you want to build around distribution, normalization, min max, right? So and that's a good topic. And again, this is that'd be a good interview question, actually. Here's the data set. Do I standardize? Do I normalize? Do both? Most people will fall into the trap of like, well, you normalize this and you standardize this. No, it depends on, like, for most of these models here, we're going to use a regression model. So standardization will work fine. If you want to use distance metrics, we might want to use normalization. But that's a good interview question, because it's a bit of a trick question, because it depends, like everything else in life, it depends on context. All right, where are we here? We're already pretty much at the end of this. So here's standardization. I'm answering the question without realizing I have code to answer the question. Sorry about that. But I pretty much covered standardization, because what are we doing here? We're going to, what are we doing here? Z-score. So I got that right. And this is confusing. Standardization is also known as Z-score normalization. I got to remind myself not to write that, because I'm just confusing the heck out of you guys. There is a difference. So what are we doing here? So again, enough talk. Let me show it to you. So what I'm trying to do here is build a histogram. And remember, I was showing you that standardization here. You want something like this. If I build a histogram around this here, you see before, like price, bedrooms, bathrooms, there's no kind of distribution here. They all look flat. And now what I'm doing here is I'm building this kind of distribution, at least for bedrooms anyway, and trying to build a distribution around that. So now you can see it's kind of got some kind of something that looks more like a standard normal curve there, based on the data we have here. And I'm doing that by creating some bins and using this, getting the mean. So to standardize, you subtract the value, you subtract the mean, and you divide it by the standard deviation. That's how you get that's how you perform standardization. And again, look a little more into that. Maybe I'll write up some more notes on that if that's confusing people, but I don't know. I don't want to get you kind of like too confused about it, because it is a bit of a nuanced topic. And here's this one here. And I give some more examples about standardization. So here, again, you can see this is not it's not normalized. It's not stuck between 0 and 1. We're going to, you got some negative values here. You got some values beyond 1. So this is standardization, right? Because again, it's not between just 0 and 1. Instead, but it's not random values. You're basically building it around a distribution, or actually the next notebooks has a better example of it. You're building it around some kind of a distribution like this or whatever. So let me zoom on to the next notebooks, because they're kind of important as well. But there's the notebook. So you already know filtering. So play around with filtering, because I want to skip through this pretty quickly. It's mostly about stuff like that. Filtering by columns, by rows. Kind of fun stuff to do. And grouping data. Very, actually, let me get this data in here so I can show you how some of this works. What is wrong with that? Am I out of credits here or something? Or am I just losing the connection again? Why is this not working? Someone changed his notebook. Should be fine. So why is this notebook not working for me? I should not have to do a pip install. I usually don't. Ugh. Shouldn't have to do that. Yeah, so if sometimes you're using a notebook, you have to do a pip install to force it to install a given library. So now I've pipped installed it. Don't know what the heck's going on here. As we said last week, if you can't figure it out, nah, Pandas couldn't have installed. Sometimes you want to do is, yeah, it's my environment. So what if you see this error? Gemini's not helping me. Sometimes it just can't help you. It's not a circular error. Tools. What I want to do here is restart the session. Might do it. Maybe not. Yes. Sometimes you're smarter than AI. Usually not. But today I am. All right, so I don't need that line of code anymore. I fixed that. So yeah, filter by column. La da 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 da. So what do I want to get down to here? Merging, results review. Yeah, I'm going to skip through this notebook. You guys can play around with this yourself. Nothing super exciting here, because I want to get to the last notebook if I can. That's more interesting. So a lot of times when you're profiling data and trying to understand what the data is, you want to use data visualization. That's definitely more interesting. And here again, we can use summary statistics. We can look at the columns and all that kind of stuff. And we're going to use a, I've imported this library. We want to start plotting this data out. So to do that, we kind of have to understand what our data is. Because remember before, like if it's not a float or it's an object, you can only do certain kinds of visualizations on it. So you want to understand your data types. It's kind of a first rule here, right? So understands what different data types you have, and then once you know that, you can figure out certain things. So if I have numerical data, I can do something that's pretty cool, which is a histogram. And a histogram is kind of taking numerical data and bucketing it. So here, for example, we're going to plot a histogram, and we're going to give it 50 bins. So if the house price is between 30,000 and 700,000, we can create 100 bins, or we can create 30 bins, right? So I can change this value here, and we get something like this. And now we have a good idea of the distribution of the data. We can see we've got lots of house prices between, say, 150,000 and 250,000. We have very few between 0 and 30. And we have only a few over, say, 400,000. So again, those of you who know your statistics, you can see there's a bit of a distribution here, but it is right skewed, right? So just by looking at this data, I can tell, because you expect certain data to be right skewed, other data to be left skewed. So this should be par for the course. So just by looking at visualization, you can tell straight away if a given feature, in this case, the feature being house price, is skewed or not. And here I go through some more details on how to do that. So yeah, you can alpha, that's just opacity. You want it to be, you make that lighter for a visualization, and the color you want it to be, and then the number of bins. And then I keep talking about this line. So this, what we want to do is draw what's called a KDE line. Kind of gives you a better idea here. So for that, we're going to switch to a different library called Seaborn, and similar library, but kind of a slightly different attributes or arguments here. And here we're saying the KDE line equals true. And when you run that, see the way it puts a nice little distribution here. And now we can actually see the tail, because this one has this is a short tail here, or no tail, and it's got a very long right tail. And, you know, helps again to tell you what kind of distribution you have. Like that's definitely not a normal distribution, and it's not uniform. And it looks more like a right skewed distribution, which again, if you take our statistic course, you'll understand, you know, it's not necessarily a bad thing that data is right or left skewed, because I expect this data to be right skewed. And if it wasn't right skewed, I'd be a little worried about it, because there's no such thing as a negative house price, right? So you don't want left skewed data into negative zone, for example, or maybe it is. Maybe you're doing social housing and you're saying the maximum house price is supposed to be 30,000. So you expect the data to be shifted left and skewed. So again, it depends on that. Something we looked at a lot last week was looking at the correlation, the linear correlation between two variables. So let's say I want to, and we talked about the size of the house. Generally speaking, the larger the house, the more expensive it is. And here we're using a scatter plot. And sorry, I should slow down a little bit here. But for this one here, we used Plotly. And we're basically saying, here's histogram, create a histogram here. And there are the arguments for it, and then give it a title, a label. For Seaborn here, we're saying make it a hist plot, slightly different name. And then we're back to Plotly, and we're basically calling it scatter. And again, this is the great thing about a data frame. You basically just pass it the data frame, and you tell it which two columns you want to plot. I want to plot the living area, the size of the living area, and the sales price, and give it a title. And now you can see you got this nice plot that's generally positively correlated, meaning as the size increases, the price increases. Not positive if you're buying a house, but and you see now we can see better. Unlike a box plot, we can see the outliers here, right? And also we might want to see this. So again, we use a slightly different line, but we use a KWS here. So here, I don't know why they use different names, but instead of calling it scatter, Seaborn calls this a regression plot, which is technically a more accurate name. And we're saying we want a KWS line, which helps you understand the regression line. And then see here how these outliers are pulling this line wider. Like they're increasing the band of it, as do these here. But you can see here, it's pretty well clustered around a certain area, and then it gets kind of gets wider. So again, these are very useful plots, and trust me, when I was a data scientist working this stuff day in, day out, I was plotting stuff like this, like not just one plot, but looking at 50 plots like this to figure out what's going on in the data. So very common to troubleshoot your data and understand what data you have by just drawing plots, because I can see straight away I got some outliers here. And then we talked about, you know, normalizing and standardization. Well, before you do any of that, you want to look at the distribution of your house, right? Because it could be kind of informative to say, well, I'm going to standardize and normalize this, but first of all, let's see what kind of roof does this house have. So what you do here is what you're creating here is just a very simple plot of counts, right? A bar plot. And of the 1,460 rows we have, what most of them are gable. I guess that's that kind of slanted gable. One's a flip, one's a flat roof. Gamble. I have no idea what a gamble is. Don't know what that is, and I think I know what a shed is. No Irish jokes, by the way. And yeah, so you see here, this is very useful by just plotting this stuff out. So visualization, it's not about just fancy plotting. It's very much about how do I understand, like, how do I want to act on my data, and why do I want to standardize and normalize it? And here's everyone's favorite is correlation, because, okay, I have 81 features, possible features. And my target feature, remember from Thursday, we talked about target feature. I have 81 features, and the target feature is the sales price. Which of those features, when I'm looking to sell a house, which are the most important features? Do you ever go to a real estate show and people tell you the number one thing you need for 2025 when you're selling a house is to have X, right? During COVID, it was a home office, and you see all these houses with a home office. If you live in the sunny part of the world, Spain, South America, Southern California, Florida, having a pool is very desirable. In New England, trust me, I have friends who have a pool where you can only use it 3 months a year. In the Boston area, like, having a pool is a disaster. It's high insurance. You have to maintain it. So you're basically maintaining this thing for 9 months of the year, so you can use it twice a month for 3 months. So features are all relative. So how do you know? So again, pool may be great down in Florida, but bad in New England, in Boston area where I live. And how do you know? Don't guess yourself if it's a good feature or not a good feature. Let the price help you. So if you notice that the distribution, when you look at prices, if there's any kind of impact from if it has a pool or not, is it causing the price to be positive, negative? It doesn't matter, right? How do you do that? Well, you do correlation. And correlation, very simple concept. It's a value between -1 and +1. If it's from above 0 to +1, it's positively correlated. If it's below 0 and -1 is negatively correlated. And negative correlation, by the way, doesn't necessarily mean a bad thing. Let's say if you're doing drug testing and you want that condition to decrease. So as I give you more drugs, you're happier? No. If I give you more drugs to your condition, your fever goes down, right? So don't confuse negative and positive values between negative and positive outcomes. So very cool. What you can do is you can take your house data frame, and you can use this function called correlation. And what we'll do is correlate every value with every other value. So it'll correlate the sales price with itself and every other feature, right? And what you get is, because this can only show 20 values here, you get this like a very well-worn rug, it looks like, or smoker's lung. No offense to all the smokers out there, but anyway, you've all seen the pictures. So what you want to do is, first of all, kind of narrow this down so it doesn't look like pitch black. So what I want to do here is, oops, did I break it? Dang, I broke it. I should have done that, because I meant to run this whole thing here. Runtime, run all. So where am I breaking? It doesn't break here. It doesn't break here. It doesn't break here. Yeah, so it's going to build that correlation map. So what I want to say here is, what do I care about? I care about my sales price feature, right? Because this is a labeled data set, sales price being labeled. I care about sales price, and I want to know which features or which columns have the most impact on sales price. And let's say I want to know the top 10. So here I'm saying here is, what I'm doing here is I'm getting my correlation matrix. So I have that 81 by 81 because I'm building a matrix, right? So it's correlated with everything itself. So I have this kind of worn out rug here, but there's too many. So I'm putting that into a data frame. Now I'm saying is the thing I want to correlate it around with respect to is the sales price. And so I'm taking the sales price and see that little distribution there. That is just one column. And then what I'm doing here is I'm sorting it by everything that's correlated with sales price. So whatever the top values are, the top values for correlation with sales price. So just sales price versus 81 other values, including sales price. So how does that look here? So here you have this correlation matrix. So this diagonal here is going to be 1 because everything is always correlated with itself perfectly. So when you look at a value of a garage area, it's 1 here because this is garage area here, 1 and 1, right? So the thing for us to look at is look at sales price, right? So we can see here that sales price has a correlation of 0.79, which is very highly correlated, which is a high number because that's very close to 1 with overall quality. Second most correlated value is garage living area. Kind of hard to read from top to bottom. And then remember we said before it's very weird, but the number of the number of garage spaces you have has got a very so this is our top 10. So these 10 features, if you only had 10 features, these 10 features will mostly impact the house you price. So that's why when people tell you when you're selling a house, make sure it looks really good. Can't change the square footage, but you know, and the more bathrooms you have, the better it seems, right? So see here, 1, the red means red hot, highly correlated. Blue means ice cold, doesn't do that. But you don't see that blue here because we haven't done it for sales price. But you can see it for other values. So here you can see here, living area 0.2 is negatively correlated with year built. So basically what they're saying is the size of the house has nothing to do with the year it was built, which makes sense, right? Right, makes sense. Whereas garage living area has, like, look at here, 0.88. Garage area is very highly correlated, 0.88 with garage cars. Like, so, you know, if you're going to fit 5 cars into a garage, you got to be sure it's going to be pretty big. Otherwise, you're driving a lot of Fiat Unos or something like that. So yeah, so that's the correlation heat map. And don't worry, the standardization, the normalization, the heat map correlation, we'll be getting into that on Thursday when we actually go into machine learning modeling. So again, this whole 2 hours plus was more about understanding data prep to get the data ready, because I'm giving you a well-curated data set, but for a lot of data sets we work on, they won't be well-curated. So that kind of wraps up today's lesson. There is a few more exercises. So again, what I want you guys to do is, like, it's great that you can open up them, but when you have time this evening or this weekend, go through these notebooks yourself. And, you know, remember Gemini, ChatGPT can do a lot of this work for you. But if you want to be an AI expert or data science expert, it's fine to have ChatGPT and Gemini again do this for you, but you have to understand why it does what it does. We'll see next week how we can just give it a prompt and it will do the modeling on this data set. But if you don't understand why it's doing what it's doing, and don't. So my advice would be, you know, read this document here, and in your AI Plus bundle, you should have a statistics and probability as well, a small course in there as well. So check that out. Kind of very important. And it's, again, I'm not talking about taking a whole course in statistics like you would back at university. I'm talking about at least spend 3-4 hours understanding the basics. Because as long as you know there's something you should do, like thinking about, should I normalize this data? Should I standardize it? Should I describe the data? Should I do a correlation matrix? If you're doing regression, you know, when should I do certain things? And is the model doing it? And look, the model can do stuff right. Like that, sorry, the large language model can do stuff right. But again, you know, when you go for an interview or your boss asks you to explain why the model is working or why it's not working, your excuse is, well, the LLM did it, right? Like, you don't want your job to be replaced by LLM. So make sure you can explain why the code works. So that's why we don't start off by just prompting this, and then the slides will be there as well. But what else was in the slides? Yeah, we just had some resources in that. Yeah, the rest was the same. All right.